Good afternoon, everyone. Thank you for being here, and also thank you for giving me the opportunity to speak here today. My name is Vasiliki Georgoula. I'm a civil engineer and the BIM Coordinator at SSF Engineers. It's a German company specializing in structural engineering and infrastructure planning. So today we are going to examine one of the most fascinating projects currently under construction in Munich. It's the second S-Bahn core line, and in particular one of the stations, the Marienhof station. Now this station has a lot of noteworthy features, BIM-wise or not. Today we will focus on the workflow that was developed in order to implement 3D reinforcement models. In the last months, we have seen a boom of innovations in the construction industry with artificial intelligence and various other applications. And this happens at a moment when the construction industry has not even yet digested the idea of BIM. Yet somehow BIM is already considered old history, which couldn't be more wrong. Creating innovation is important, but it's equally important to make innovations happen, make them reality, and eventually make them standard. Best example known to us all, our beloved AutoCAD. Few years back, it was considered cutting-edge technology, revolutionizing the industry. Nowadays, it's just a standard tool. And that's absolutely fine, because innovation is only successful if it's not considered innovative anymore. So I hope this session today will help or will serve as an inspiration of how we can work together towards this direction. Few people have been already to Munich. I hope you didn't miss this famous landmark. It's the new city hall in the center of Munich, in Marienplatz. Next to it, you already see the construction site of the Marienhof station, which has approximately the size of a football field, let's say. Here's a small overview of the whole project. Here's a city map of Munich, and the green line is the existing suburban train line going from east to west direction, crossing the center. And currently, trains arrive at the Munich main station every 1 to 2 minutes at peak hours in each direction. And this makes it the existing core line one of the most frequently used lines in Germany or even in Europe. The suburban train system was designed originally in the 70s for 250,000 passengers daily, and this number now exceeds the 800,000 passengers daily. As a result, in order to release the pressure on the existing core line, a second core line is to be built, and you see it here, it's the red line. It has the same direction from east to west, going through the center. And the heart of the new line is a 7-kilometer long tunnel from Munich main station to Munich East, with Marienhof being the intermediate station. Now, about the station itself, there are only 3 points I would like you to remember. The construction method used was a classical diaphragm wall, top-down method. The station has 5 levels, with the platform level being at the depth of 40 meters under the surface. Here are some pictures from the construction site, because everything looks small in our computer screens, but the actual dimensions on the site are very impressive. You see, we have already reached a level of the excavation level of the -5th level, so it can be even a little bit claustrophobic to be down there. About the project, everything is planned and designed with BIM. We have structural, architectural, MEP, as well as other construction-related models. And as a logical consequence, we decided to model the reinforcement also in 3D, since the advantages of BIM planning also apply to reinforcement models too. We will talk about that a little bit later. Now, we started off with simpler structural components like these beams on the left, soon moved on to more complex ones like slabs, or even challenging geometries like this tunnel connection. Here you see an example of a reinforced slab. So let me tell you, of course, at the beginning there were some challenges with the modeling aspect, the software aspect Also considering the complexity of these components, for example, this slab is 1.5 meters high, almost my height. It's highly reinforced. Often we have 6 layers of reinforcement at the bottom, 6 layers at the top. Also remember, because of the top-down method, slabs are constructed before the walls and not the other way around. So we need to provide connecting reinforcement for the walls underneath and above the slab. So there are complexities, there were challenges, but they were in the end minor challenges because we were very soon able to create 3D reinforcement models without extended problems. Also, the BIM information content about the classic content, let's say, applies also for these 3D reinforcement models. We have information about the rebar numbers, the diameters, the lengths, the layers, the end treatment descriptions. Is there a coupler or a hook at the end of the rebar? So everything is included in the model, which makes it very easy to create lists, tables, and views according to these parameters. So far, so good. We have 3D reinforcement models. How do we proceed? What do we do with these models? A few words about the conventional reviewing workflow. It looks somehow like this. We, the designers, we produce statics and reinforcement drawings for the building owner, which are then reviewed and checked and approved by an external structural engineer. After the approval, the reinforcement drawings are delivered to the contractor, the reinforcement is installed on the site, and in the end, the site supervisor comes, documents the installed reinforcement, and the reinforcement drawings are archived and become part of the official construction documents. So as you can imagine, the whole process is plan-based. And there are compatibility issues with 3D reinforcement models, mainly in a bureaucratic sense. For example, there are no regulations about digitally stamping models, digitally signing models for official approval, or there are no regulations yet for including models in the official construction documents. Until now, only CAD files or PDFs are allowed. Also, let's be honest, going directly from 2D reinforcement plans that have been used for 100 years to having a rebar model on an iPad on the construction side of this complexity seemed like too much of a big step. So we try to be realistic, and we try to find a middle solution, which are simplified drawings that accompany the 3D models. For example, you see here one of them for the slab. There is a view of the layout of the reinforcement. There are some rebar tags and dimension lines because it's easier to have this dimensioning instead of having to measure the dimensions on the 3D model every time. On the other side, there are no rebar shapes on the plan like in the conventional reinforcement model because the rebar shapes can be easily seen on the 3D model. There are also no sections on the plan because with the 3D model you have the possibility to make dynamic sections wherever you want. But the simplified drawings have a very traditional sheet layout that is perfect for stamping. And since they are quite minimalistic, they are derived from the 3D model in a quite semi-automated way and quite fast. Now, don't get me wrong, because these simplified drawings are by no means real reinforcement drawings. They are not sufficient in order for the reinforcement to be installed on the site. On the model on the other side is not capable of going through the review process alone for the moment. Only the combination of those two can actually work. So now we have different working material. Instead of having 2D conventional reinforcement drawings, we have 3D models plus simplified drawings. So we also need to adjust the reviewing workflow that now consists of 2 phases. In the first phase, we upload the model on a common data environment. It's a platform with a 3D integrated viewer where all parties have access. And then we set up a meeting with a designer the building owner, the contractor, and the site supervisor, we sit at the same table, we navigate through the model together, and we discuss points like the following. Installation sequence of rebars, especially in the kind of complex areas. These kind of small films are very helpful for understanding the installation sequence or even finding out if the installation is even possible. We discuss adding or adapting installation bars. Here you see an example highlighted in green. We needed to add some small stirrups or some small hooks to make everything more stable, let's say. We discuss points like these high reinforced areas where concrete could be a problem. You see here 6 layers at the bottom and at the top. We modeled concreting openings like the green one to make sure there is enough space for the concreting. In some cases, we even needed to leave out some rebars so that there is space. Or we discuss points like changes in the layout of the reinforcement. Here you see an example of 2 connecting parts. They are connected by overlapping rebars. It was discussed if maybe we should use couplers so that there are no rebars sticking out of the concrete and there is more room for people and machinery to pass through this zone. And many more points, but I guess you understand the things that are discussed in this meeting in this sense. Now, the second phase of the adapted reviewing workflow looks more similar to the conventional one. After we implement the wishes of the contractor in the reinforcement models, and then they are re-uploaded in the CDE, this time together with the simplified plans. The model is reviewed and checked by the external structural engineer, and then the simplified plans are stamped accordingly, like in the traditional sense, and they are archived, and that's how the review process is completed. Now, for the construction side, there is no extra step needed in order to deliver the plans on the site or something like that, because of the so-called BIM kiosk you see here in the photo, which is nothing more than a computer with a big monitor connected to the CD. It's a very inexpensive solution, and the models are from the beginning in the CDE, meaning that they are for the very early design phases on the construction side too. The reinforcement is then installed on the site with the help of this BIM kiosk, with the help of the 3D models and the simplified plans. And as you can imagine, such a BIM kiosk on the site can improve understanding of layout and improve communication on site. Coming already to the conclusions of this session, I would like to highlight some advantages and disadvantages, starting with the dark side of the moon. So we have seen that the regulatory bodies need to work and develop regulations that support this kind of BIM workflows. Or we have seen that existing workflows are not relevant anymore and they need to be adjusted or even reinvented. There is a steep learning curve for all parties involved, which unfortunately leads to higher initial costs. This is a very typical disadvantage of BIM, but the bright side outshines all these disadvantages, in my opinion. We have seen that this workflow is very transparent, streamlined, meaning that from the very early design phases to the execution until the reinforcement is installed and documented, there are no communication gaps. The contractor is involved in the design phase very early, but most importantly, very actively. And of course, with the 3D reinforcement models, there is better understanding of the layout, which leads to faster reviewing and checking, not only for us internally, for the designers, but also for externals, for the contractor, for the external structural engineer. And all in all, the whole workflow leads to a more detailed, accurate, and less error-prone design. This is the last slide of the presentation. So I would like to repeat what I mentioned at the beginning of my presentation. It's not about 3D reinforcement. It's about making innovation standard. And here you see the Gartner hype cycle shows the path of innovations. It starts with a technology trigger, which is soon followed by a peak of exaggerated expectations. This innovation is amazing and it can do so many things, this and that. We are so much faster, so much better quality. Unfortunately, what comes next is the crash of disillusionment. It's the point where we realize it's amazing, but we need to learn the software and it takes too much time, it's too much effort. It's amazing, but we need to train our people. It's amazing, but there is bureaucratic barriers, or it's amazing, but it costs more. That's why this is a critical point, because a lot of people give up at this point. And that's why the next phase is, in my opinion, the most important one. The path of enlightenment. It's the phase where we need to realize that, first of all parties involved need to sit together, contractor, site supervisor, building owner, checking engineers, in order to, first of all, recognize the advantages of the innovation. It's not about reinforcement, it's about innovation. Recognize the advantages, recognize the barriers, and try together to find solutions to overcome those barriers, because only then we can really reach the plateau of productivity. Thank you, and have a good day.